All right, welcome to this week's Chem Weekly Review. So this week was mostly alkane naming, Newman projections, all of that fun stuff. So I put in a lot of questions on this packet. Will we get to all of them? No, I just made some extra ones for y'all to practice with. I'm going to try to go through a couple of each type, and then maybe if there's a specific type y'all want to go over specifically, then we'll go over those. So, yeah, this is being recorded. We don't know when we're going to actually put on the recordings, but they will be on eventually, and then I'll let y'all know when they're up. But just FYI, like if you talk about your grades, it'll show up in the recording. So if you don't want people to know about your grades, don't talk about them. All right, so let's go ahead and get started with structure naming. So structure naming is really fun. It's all about IUPAC. All about IUPAC, how we number and choose the way we number. So the first one is A. That is definitely not the first one. Hold on. Oh my gosh, did I lose like an entire slide? Oh, no, that's the wrong. Oh, here we go. Okay, so let's look at A. So the first thing we want to do when we do this is we want to decide what is our biggest substituent, right? Because remember we have something like, hello, don't forget to sign in. All right, so we have something like something hexane. Or something like that, right? So we need to decide what is our root word first. And so let's look at this one and decide, okay, so what do we think is our root?
Octane.
Octane, okay. So how did y'all get octane?
The longest 8 carbons.
We have 8 carbons as our longest chain. So I'm thinking 1, 2, 3, 4, 5, 6, 7, 8. What do y'all think?
Yes, but number the other way.
Okay, why would I number the other way?
Because it's a smaller number where the first substituent is backwards.
Perfect, right? So we don't always just blindly number left to right. We need to make sure that we're numbering with the substituent at the lowest position. So instead of going this way on the paper, we're going to go this way, so my substituents are lowest. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so now let's talk about my substituents. What substituents am I dealing with here?
Methyl. A methyl.
Okay,
And an isopropyl.
perfect. Do y'all understand propyl? Do y'all understand why it's called an isopropyl?
What branches off out like
Yeah.
that?
Yes. So so it's 2 parts, right? Iso and propyl. Propyl just means 3 carbon, and then iso means that when I'm attached to it, I get equal parts. So I get 1 on here, 1 in here, and 1 in the middle. So that is an isopropyl. All right. So I know that the 8 gives me. Okay. My pen did something weird. Okay. Oh. Well, that's cool. Okay. Anyway, so the pen gives me octane. And then I have 2 substituent groups. Okay. So how would naming work?
5 isopropyl and 3 methyl.
Why shouldn't I go 3 and then 5?
Wait, I thought you do it by is it the
Alphabetical order, right?
Alphabetical.
Yeah.
So which goes before which?
Methyl goes with
It's HIJKLM.
iso
So
counts.
So
So
which
the
one
iso
goes
count-
first?
Iso counts.
That's what it
ISO goes first. So learn your ABCs. Every time I do this, I have to go through my ABCs, unless it's like etho and it's easy.
No, I just wasn't sure if the ISO counts.
The ISO counts. So When you do something like dimethyl, trimethyl, don't count.
Okay, that's what I was confused.
But when you do tert, iso, sec, those things count. Okay? So when I do iso, that counts as part. But for example, here we might have a dimethyl, a trimethyl, something like that. Then the tri does not count. Okay. Good point. Okay, so iso goes first, and iso is attached to the 5th carbon. So I go 5 isopropyl, and it's comma. Wait, is it comma? I don't remember. It's dash, yeah. Sorry. 3 methyl octane. So this part, one part, one part, one part. So 2 substituents, and then 1 root. Questions? All right, moving on. Let's do this next one. I'm going to go ahead and count my carbons. Okay, so I'm going to start 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be my longest chain. What do y'all think about that? No? Y'all don't think that's my longest chain? What would my longest chain be?
Or the 6s
And
go up.
I would go up, right? So remember, just because, so again, we don't assume we go left to right. We also don't assume just because it's a chain on the horizontal, it's going to be the longest possible one, right? So if I go this way, I get 7, 8, 9. Okay? So we know we have our longest chain, right? There isn't another way to get the longer one. So here's another question. Which side do I want to go from? Currently, I go 1 to 9 this way. This way? Should I go the other way?
Other way.
Other way? Why should I go the other way?
The numbers end up being smaller all around. You go down.
Perfect, right? So just because I have a methyl here and a methyl here, still, yes, I have them on ones. But if I go the other way, I still get lower numbers. Does that make sense?
Mm-hmm.
So there's a lot of considerations when y'all do this. And hopefully y'all don't get such a weird question on the test. But, you know, we want to be prepared. Okay, so I'm going to go top down. 1, 2, 3, 4, 5, 6, 7, 8, 9. Does that make sense? All right, so on my groups, I have 2 methyls. I have 1 ethyl. I have one of these things, and what is this called?
Isobutyl.
Is it isobutyl? What does isobutyl look like? Okay, so I do have 4 carbons, so we definitely get butyl, something. But an isobutyl would look different. This is what we call a tert butyl. Tert butyl. A tert butyl is basically how we get tertiary carbon, right? So this is a
That's right.
this is
I
a
was I was thinking it the same.
this is a tertiary carbon. And because we have it, we have a tert butyl group.
So how would an isobutyl look?
I don't think we have isobutyl
No?
groups. Wait, no, we do. It would be 1, 2, 3, 4. That's an isobutyl.
Yeah, where it has that same fork.
You when you get the isos, you always get that like equal ending thingy.
Okay.
And so, all right. So if you had a sec butyl, it would look like this: 1, 2, 3. That's called a sec butyl. Just a preview of upcoming
It's
introductions.
off the second carbon.
So you can
Yes,
just write it
perfect.
as T-butyl, like you don't have to put tert or.
Yes, that's my lazy method. Most people just call it T-butyl, and people know what it is. I don't know what your professor would prefer. If they really want you to spell it out, spell it out. But I've never spelled it out, and I've done okay. So here's hoping. All right, so I have first of all the chain. What is my chain going to be called?
No name.
No name.
No name. Perfect. All right, so let's go. Again, we want to alphabetize. So what group goes first? Ethyl. Okay. Why ethyl?
E.
But I have a B for butyl.
But the tert counts, right?
The tert counts. Correct. So, just because I have butyl doesn't mean it goes first. If I had dibutyl, then which one would go first?
Oh,
Butyl.
the butyl.
The butyl would go first because di, tri, don't count. Tert, sec, iso counts. Okay, so let's go. No. Okay. All right. So my ethyl is on which carbon? 5. Okay. So I have 5 ethyl, and then I have which one goes next?
8 methyl.
Okay.
2, 8, dimethyl.
I have 2 methyls,
Oh, yeah.
so we need to keep track of both. So it'll be 2, 8 dimethyl, and then I have 4 tert butyl purple no name.
That's a long one.
Yeah, I realized that I didn't exactly give y'all space.
Nah. I was thinking that, but I wasn't gonna say it.
Let's just say I sat on my computer and made these, and I was like, let's add more stuff. So
It's appreciated. So
I didn't exactly think of space on these papers. But hey, like keep it in your notebook or something. Any questions about how we got there? No? All right, perfect. All right, so I want to get to Newman's. Those are a little harder, and those are question 2.
Okay.
So if y'all don't mind, I'm going to jump forward. I'm going to go Newman's, and then I'm going to do cyclohexanes. And let's come backwards, because
Okay.
I want to make sure we cover everything. This stuff is very, very important, and drawing is hard.
And we have a quiz Thursday.
Y'all have quiz Thursday, so let's cover as much material, and then come back for what y'all want to talk about. Okay.
This will all be on the quiz.
Yeah,
Oh, will it? Ooh,
I
fun.
think so.
All right, well, we're going to skip, preview. Okay, so we're going to do Newman projections. All right, I personally love Newman projections, and so this is going to be really fun for me. Okay, so Newman projections. Quick overview, right? When we have this, we have a front carbon, and we have a back carbon. And it depends on how I look, okay? So if I have something like this, and I look this way, I have front, back. The carbon that's in front and the carbon that's in the back usually matters. They will have an arrow if they want. They will have an arrow if they want you to specify. Sometimes if they don't really care, sometimes they do care. Just make sure you do whatever they want.
So the arrow is the front.
The arrow is going to be the front. This is basically your eyeball looking this way.
Yeah, okay.
This is my eye looking that way. It's looking down. Okay, that's weird. Anyway, okay, so, all right, so I'm going to be looking this way. So what is my front carbon going to be? The one with the bromine or the chlorine? The bromine. All right, I'm going to make that blue. And then my back carbon is going to be chlorine. I'm going to make that green. Okay, so when I do this, I have a look. And I do this very methodically, and so I hope that y'all will understand how I do this. And the thing with drawing in OChem is the more organized you are, the better off you are. If you're not organized, you're going to get confused. So if you're really organized and do things exactly the same way every single time, when you're on the test, you know what you're doing. So if we look at this, we have a plane, right? So remember how we talked about when it's like a straight up line, it's going to be in the plane, and when I have dashes and wedges, it's in and out of the plane. All right, so I have something in the plane. So when I have something in the plane, so in Newman projection, let me just draw a generic Newman projection, right? I've got okay. So this is a Newman projection. The front carbon is the dot. the back carbon is going to be the circle. Okay? So, when I do a generic Newman projection, what I always want to do is I make this line the plane. Okay? That way I can just look at my molecule like this, and I know inside of the page, out of the page. If I make this plane, if I make this line, the horizontal vertical line, it makes things way easier, right? Because now I can just look at it, for, like kind of do a little perspective change, and I know what's on the right, what's on the left. It makes your life way easier. Okay. So what that means is setup matters, okay? There are two orientations of drawing Newman projections, okay? So my front carbon can be oriented this way, or it can be oriented this way. My back carbon will be oriented the other way. Do you understand the difference between the two orientations?
Yes.
Okay. So what I want to do is when I draw my generic Newman before I start adding my substituents, I want to make sure my orientation matches. So if I call this orientation A and orientation B, what orientation matches this molecule? Is it going to be A or B?
A.
Why would it be A?
Because it looks like a Y.
Yeah.
Yeah. So the reason why is because my in the plane goes down.
That's why? Because your in the plane goes down. I never knew.
Yeah.
Because this molecule, the carbon that's in the plane is facing downwards. In other words, the two not in the plane ones are facing upwards. So it's like a Y, right? It's basically like a Y.
Yeah.
Right? So, for example, well, that one's going to be exactly the same. Let me find one that's different. Okay. So, for example, this one, the in the plane goes up, up, and these two go down. So this one would be this.
Oh.
Does that make sense? Okay, so basically when I draw these, I want to be very, very organized, right?
Yeah.
So, here, look at how in the plane, the one that's in the plane, is facing downwards. Here, this one, the one that's in the plane, face downward. Down, down.
Now, Timothy, if you mix them up, but not you, yourself, a person, would it actually come out wrong?
No, it wouldn't. You just have to, it's just a little more legwork.
Okay.
Science is for lazy. Well, the reason why we have science is because we want to make things as efficient as possible. This way is just, I try to be as lazy as possible when I do this, because it lowers your chance of error. The more times you have to keep track of things, the more errors you're more likely to make. So just keep it really simple, right? Down, down. There's people who try to do like the whole like up, and then I'm like, why are you rotating now? Okay, so look at how this one, up, up. This is the front carbon. Look at how this one's going up, up. There's a difference. Okay, perfect. So, going backwards. All right, so, do y'all mind if I erase all this? All right, cool. So, none of this is useful anymore. Okay, so let's talk about this specific carbon. Okay, so, I'm going to draw my generic Newman. I'm going to make this one blue, just to make it easy. Okay, so my front carbon is going to be downward facing, like this. Okay. My backward carbon is going to be upward facing.
Now, if your back carbon had been turned, or like if your chlorine going into the page had been up, matching the bromine, it would be an eclipsed drawing that we would do?
Yes. Yes. So, for example, this is asking for as shown, so this is going to be as shown. So, if it was like that, it would be an eclipsed position.
Okay.
And so, you would draw it, if they want as shown, they will want you to draw the eclipse version.
So that's going to be something we need to pay attention to.
Generally
Reading
speaking,
the questions.
they won't ask you as shown. I just drew as shown because that helps you like logically think through how do you draw it. And then we'll talk about how to change it into your most and least stable conformations.
Okay.
So, blue is front, green is back. So, on the downward face, so let's do the horizontal plane carbons first. So that's going to be this one and this one. So, In my front carbon horizontal plane, what do I have?
Methyl.
I have a methyl, right? So all I'm going to do is write CH3. Makes it easy. We know what that is. Okay, my back carbon horizontal plane, what is on it?
Benzene.
Benzene. Okay, so I'm just going to draw it out. Okay, so now let's talk about right and left. So I'm going to, again, look at my carbon, and I'm going to look at it. So currently it's on the page, right? I'm going to pretend my page is facing me, and I'm looking at it this way, right? Like the page says I should look at it, okay? And so what is going to be out of the page is going to be on my right. So out, right, in, left, right? Whatever's facing out of the page is going to end up on my right. Whatever's in the page is going to be on my left. Does it make sense? If I looked at the paper, for example, if my question was having me look at it this way, in is going to be on my right, out is going to be on my left. So perspective matters. Make sure you know which way your arrow is going. Keep it simple. Okay, so I know out is right, in is left. So on my right, what am I going to have? My ethyl. And then on my left, what am I going to have? Bromine. Perfect. Okay, I'm going to do the similar thing for the back carbon. What is going to be on my right? Hydrogen. And what is going to be on my left? Chlorine. Does it make sense how I got there?
Yes. Yes.
Remember, step by step, have a system. Newman's, Fisher's, like all the weird projections y'all do, having a system will make life really easy. Especially on a test when you're trying to think about a lot of things. Okay. So, now what we want to do is switch to our most stable conformation. So, if I want to switch to my most stable conformation, what does that mean?
Isn't that the one where the biggest groups are the furthest apart?
Yeah, so basically what we want to do when we do stable conformation is we want to keep our biggest groups as far away from each other as possible. So we got to change it, right? We're not in our most stable conformation because our benzene is right next to our ethyl. So not most stable. So this is going to be as shown. And not most stable. Ethyl next to phenyl. Okay, so let me go ahead and draw out our most stable conformation. When I do this, again, let's keep a system, let's stay organized, okay? What I want to do when I do most stable conformation, or whenever I rotate my Newman projection, you only move one carbon, okay? That means I'm not going to take both carbons and start rotating them simultaneously, right? All that's going to do is confuse me. So I'm going to keep my back carbon. That's my habit. I always keep the back carbon stationary, and I rotate my front carbon, okay? So first things first, I'm going to do most stable. The back carbon is going to remain in position. So my benzene stays in the front, on the top. I have chlorine, I have hydrogen. Okay? And now I'm going to rotate my front carbon. Okay? Now, I want my biggest group to be as far away from the biggest group on the back carbon as possible. What is the biggest group on the back carbon? My benzene. And what is my biggest group on my front carbon? My ethyl. So I want my ethyl as far away. So when I do this, I want to get it in this conformation, where the ethyl is facing downwards.
So what a CH3 is right now?
Yes. And then I'm going to rotate everything. So ethyl comes down. I'm going to rotate this way, right? So ethyl comes down, which means CH3. Which means CH3. is going to be this way, and bromine's going to go this way. Okay? That's going to be my most stable conformation. Now I'm going to do my least stable. So, least stable is going to be the exact opposite. I'm going to put my two biggest structures right next to each other. So,
An eclipse?
yeah, I'm going to do an eclipse position and put them right next to each other to make it the least possible stable one. Obviously, like some tests will ask you to do this. I just want us to understand the concept of it. So,
I feel like he gonna ask us to do
Right.
all right. Well, then y'all are well prepared. Okay.
Yeah.
So again, I do not want to touch my back carbon. We're going to keep it the way it is. And then what I'm going to do is I'm going to first do an eclipse. And what that means is you see how I'm putting the groups right next to each other. Now I'm going to put my ethyl in this position, right, because I want the ethyl right next to it. And so this way I'm rotating this way again. So bromine's going to end up where the ethyl was. Yes. And the CH3 is going to end up where, yeah, so do y'all see how I just rotated it? So, when they're right next to each other, that's going to be the least stable position. Okay. Do y'all want to do another one, or do y'all want to go straight to chairs and then come back?
Can we do one more?
One more?
I'm sorry.
Oh, no, that's fine.
Okay, let's do another one.
Yeah.
Okay, so again, I'm going to do the same thing. I'm going to color code. All right, so this time, our front carbon is going to be on the same side. Front's going to be blue. Back's going to be green. Okay, so I'm going to do my chairs the same way I did earlier. I'm going to set it up with my front carbon is going to be facing up or down.
Down.
So my front carbon is going to be facing down, similar to the one we just did, right? This is my front carbon, and this is my back carbon. Okay, my front carbon, what is my biggest group? Oh, what's my in the plane group?
Purple. Purple.
It's a purple, right? So 1, 2.
I was like 1, 2, 3.
So that's gonna be what it looks like. It's a purple group, okay. And then here doesn't matter, but let's just do it. So on my right will be a methyl. On my left will be a methyl, right? This time we don't have to pay as much attention. It's just like right and left, they're both the same. CH3, CH3. Okay? And then for my carbon, back carbon, what is in the plane? A methyl, perfect, CH3. What's going to be on my right? My alcohol, perfect. And on my left is going to be an ethyl. This is going to be as shown. Okay, so let's go on to most stable. So, first things first, let's ask, is the as shown structure the most stable structure? No, why not?
Because your biggest groups aren't as far apart as they could be.
Perfect. So what I'm going to do is I am, again, going to keep my back carbon in the same position, and I'm going to rotate the front carbon. So let's keep the back carbon in the same position, and I'm going to rotate, right? So I'm going to rotate so that the propyl is going to be opposite. I'm rotating this way, so my propyl goes here. My propyl is where this is. My CH3 is going to be on the opposite side, and my other CH3 is going to be here. And now my two biggest groups are as far away from each other as possible. And then let's do our least stable. this way, I'm going to put my propyl right next to my ethyl. So I'm going to rotate it this way. I'm going to keep my back carbon exactly the same it was. OH, CH3. Okay, so my propyl, I'm going to be in the close position like this. Here is going to be my propyl, right here. So 1, 2, 3. My propyl is right next to my ethyl. When my propyl moves this way, this CH3 moves here. The other CH3 goes here. Questions, comments?
I have a question. When you're looking at the Newman projections and we're doing the substituents, are the propyls and ethyls larger because of the number of carbons?
Yes, remember that every single carbon, remember, when I have CH3, it's not C, it's not a carbon, it's literally a carbon attached to a hydrogen, attached to a hydrogen, attached to a hydrogen. These are big, big groups, right? It's not just one atom, right? Here we look at it and we just see a line and we're like, oh, it's not a lot.
Mm-hmm.
But you have to think of it as, it's got all those hydrogens attached to it. So it's a big group. In fact, tert butyls are huge, like gigantic. And so, like, just think, okay, like, just think about this tert butyl, right? I have carbon attached to a carbon, attached to a carbon, attached to a carbon, which is attached to a hydrogen,
Yeah.
hydrogen, hydrogen,
Yeah, okay.
hydrogen. This thing is ginormous. And this, the reason why I introduced tert butyl is actually because when we do chair conformations,
Mm-hmm.
sterics is very relevant.
Okay.
So sterics is going to be a big deal for OCHEM. And so that's why tert butyls, that's why I included it so early. When you identify a tert butyl, it's going to really help y'all later on.
Okay.
So moving on, going backwards. Okay, so everyone clear on how this works, why things are the way they are? Okay, perfect. Now we're going to move on to cyclohexanes.
Cycle.
These are called cyclohexanes, but they are the notorious chairs. So I'm going to show y'all my pro tip on how to draw chairs, because I too am very lazy. All right, so basically what I do is I draw two parallel lines that are overlapped, and then I just draw little triangles to match them up. Don't do the free-handed thingy, it never works. Okay? This way, it just looks nice and neat. So, that's the way I do it. Y'all can do chairs however you want, but y'all just see me draw it this way a lot. Okay, so I want to introduce the idea of axial and equatorial. Okay, so let's do you guys want purple for axial?
Yes.
Okay, purple is axial. Axial, and then equatorial, let's make, I'm feeling red. What do y'all think?
It's fine.
Equatorial, okay. Okay, equatorial. Okay, so the axial position follows the pointy. Okay, so axial position follows the pointy. Okay, so axial, 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 axial. Okay, every single carbon on my cyclohexane has an axial position and an equatorial position. Okay, and the equatorial position doesn't follow the pointy. It goes in the other direction. So here, 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 and here. Axial, equatorial. Okay, so let me think. How do I want to do this? Okay, let's first talk about naming chairs, and then we'll talk about drawing chairs. So, when I name chairs, we have a base, right? And so, let's go through cyclohexane. Okay, so, cyclo means circle. Basically ring, right? When I have a ring, I always have cyclo in front of my 6 carbon. So, cyclohexane just means 6 carbons in a ring. So if I have 5 carbons in a ring, what do I call it? Cyclopentane. If I have 8, octane, okay? So when you hear cyclo, you think ring. We're mainly going to work with cyclohexanes because cyclohexanes are the most stable rings in organic chemistry. So we don't learn how to draw special cyclopentane, but cyclohexanes are very special. So when I do this, all I have to do is I need to pick the position. And the positions will have priority based on the Engelbreit law. I think that's what it's called. I mispronounce it every time. But basically here, for this one at least, there is no priority, right? They're the exact same. If I were to do this one, what is the priority? The second one. Bromine would be 1, 3. Okay? So this is what we call 1, 3. So the substituents are 1 and 3 from each other. Okay? So we want to consider, for naming, position, and that's, I think it's KIP, Engelbreit. They're like the 3 people who figured out how to name these, or who designed the method. They didn't figure it out. They designed the method. And then we want to do Sis Trans. Okay? Cis means same side. Trans means different side. Okay? What that means is we can think of my cyclohexane like a little platter. So pretend this is my cyclohexane, and it's in the page, right? My cyclohexane is in the page. And it can either point up. So for this one, I have 2 point ups. In other words, they're pointing out of the page. So they're going to be cis or trans. If both of them are pointing out of the page. Cis. If I have one pointing out, one pointing in, what do I get?
Trans.
Trans, right? So this is going to be cis. This is going to be trans. Does that make sense? Perfect. Okay. So let's just go through naming. There isn't an easy way to like burst into it, and also it's relatively simple. All you need to do is remember cyclo. Remember to keep account for cis trans, and then just do the numbering. Okay. So this one will be 1. This up a little bit so I can have space. Okay, I'm going to call this one 1, 3 dimethyl cyclo. Wait, no, this is cis 1, 3 hexane. Again, there's like literally no space on the paper out there. Sorry. Does it make sense how I got there?
Yes.
Okay, let's do the second one. This is going to be trans 1. No, this is going to be trans 1 bromo 3 methyl cyclohexane. And as y'all can tell, I haven't named these things in a very long time because I thought it would take 2 inches of space, and it's probably going to take like the whole page to fill in the entire name. Believe me, when you type these things, it doesn't even occur to you how much space these names use. Okay, so trans 1 bromo 3 methyl cyclohexane. Make sense? Perfect. Everyone's on the same page. Awesome. Okay, so now let's talk about drawing chairs. When I draw chairs, we get equatorial and axial positions. Okay, so if I have a let me put a title so everyone knows what we're doing. Okay, so chairs. Okay, so when I draw chairs, I have a cyclohexane. And let's assume that all the positions are going to be same side. Okay? That means all the positions on the carbon, all the substituents, all my methyls are going to be facing up, same direction. Okay? This would be the same if they were all facing down, all the same direction. If that were to happen, I would go E, A, E, A, E, A. This is a shorthand method of getting there, okay? I just go around the circle and it's going to alternate. If all of them are facing the same direction, I'm going to alternate between E, A, E, A, E, A. However, if they're not, we're going to have to opposite it, okay? So for example, I'm going to do the same thing but with a couple switched around. So I'm going to start with this, and then with this, this, I'm going to skip one, this. So this one, I have a missing one, I have some facing the wrong direction, and on test I'm like, oh my gosh, what am I going to do? Well, we're going to do the same thing, and then we're going to do a little change, okay? So I'm going to go around and continue going E, A, E, A, E, A. However, I did E, A, E, A, E, A, E, A, assuming that they're all facing the same direction. In this case, that is not true. So I started out with E, and so all I'm going to do is the ones that are facing a different direction, I'm going to switch the lettering. Okay? So I started out on facing up, so all the ones facing down are going to get switched. It doesn't matter which one you switch, as long as they're all the same. So if I want all my facing downs to be the same, to be one, then I just switch all facing up. They just need to be on the same. Okay? So I'm going to switch this to E, this to A. And then just remember, as you go around the circle, do not skip the one that's missing a letter, missing a substituent. You want to make sure everything is covered.
So all of your downs are A's on this, and all the ups are E's?
We're not talking about up and down yet.
What do y'all mean? I mean in the page, out of the page. That's what I meant.
Right, so all of your out of the pages are E's?
No.
No, I have out of the page as A. The letters do not matter up or down. We just draw the letters. We don't care whether it's going up or down.
So on this one, 2 E's and 2 A's can be next to each other?
Yes.
Okay, so
Absolutely.
somewhere I got confused.
Why
Okay.
would you switch it? Can you explain that again? Like why we just, I guess, reassign that?
Okay, so basically this, when we do all the same side, we switch EA based on the assumption that they're all facing the same direction. Okay? Basically, as you go around the cyclohexane, if all my substituents are facing the same direction, I get some up, I get some down, EA. Okay? However, if they're facing a different direction, if they're not going out of the page, then I'm going to have to switch the lettering because now it's not going up, it's going down.
Okay. Got it.
Okay, so you started with E. And the next one became a E. And then the one after that is a E. And then the one after that is a A.
Uh-huh.
And then another A, and then another A.
Yes, I go. Okay, so this doesn't matter as much, right? So the one here doesn't matter. Like, it doesn't matter the letters. Just keep in mind you want to go alternating. E, A, E, A, E, A. If they're all facing the same direction, we alternate.
Right.
Okay? If they're not facing the same direction, I'm going to first go and alternate. Right? Have a system make sure that you're clear. You alternate all of them. And the ones that are different, I'm going to switch.
Okay, so the same EA that you did, you do that still, even though I know all of them aren't the same.
Yes.
And then
I switch.
That, and I switch the ones that are different.
Yes.
Okay, so in this case, it was the ones with the dashes, and then the one that was missing one.
No, the missing one doesn't matter. The missing one, since there's nothing, I don't have to
Okay.
worry about the
So the
lettering.
one with the dashes.
The dashes.
Yes.
I changed. Okay, so whatever it was, if it was an E, I changed it to an A. If it was an A, I changed it to an E.
Yes.
Perfect, yes.
Okay.
It'll make sense when
Yeah, it'll make
on-
sense when I start
on
doing
the
it.
chair.
It'll make sense on a chair, but I know this sounds really weird.
And that's just so like because the up ones start with the E, the bottom ones start with the E, and alternate that way.
Well, because it's on what plane, if it's an equatorial or an axial. Because you can have an equatorial go up
Yes.
and an axial go down.
Right, so for example,
Yeah, that makes sense.
this equatorial faces up, even though it's equatorial. So I don't worry too much about up and down. I just worry about equatorial, axial, and it just gets dropped on. So simple science. All right, does this make sense how I'm getting this?
Mm-hmm.
Perfect. Okay, so now I'm going to go through this, and I'm going to assign EA for my thingy. Okay, so do we want to do black? Yeah, let's do black. Okay, so again, I'm going to do E, A, E, A, E, A. Okay? I just went around and drew all my E's and my A's. Do I have any direction switching?
No.
No. So do I need to do any, do I need to cross anything out and switch them? Yeah. Does it make sense? They're all on wedges, so I don't need to do a switch, right? So for example, the second one, are they all on wedges or dashes? I have both. So do I need to switch the second one? Yes, but don't worry about that yet. Let's just go through this one. All right. So notice also how I went EA around the circle, even though some of those carbons don't have stuff. I just like to do that so I know in my brain everything's working the way I want it to. All right. So now that I've drawn my EA, it's time to do my chair. Okay. There's my chair, and I'm going to number my carbons. I'm going to call this 1, 2, 3, 4. You know, I should do this in a different color. I love this because I get unlimited colors. And it's way easier than switching markers. Okay, so here I can just arbitrarily assign a carbon number. I usually assign this one as 1 because habit. So I'm going to do 1, 2. I'm going to do this inside. It's a little easier. Okay. 1, 2, 3, 4, 5, 6. All right. So make sure, while we're practicing, we want to make sure that all our carbons are matching up. So number your carbons. When you guys get good at this, you probably won't need to number them, right? But when we practice, we want to make sure we're very clear. We know what we're doing. Be very organized. So I have carbon 1 is attached to a methyl, and the methyl is equatorial. So the equatorial position on that carbon position is going to look like this. Okay? Carbon 2 has nothing. Carbon 3 has an equatorial. And an equatorial on that one will look like this. So this is my finished carbon, my finished chair. It's actually kind of long, but you know, it's okay. All right, so this is going to be my chair conformation. Now let's ask a question. Is this the most stable? Yes. What would be the less stable version of this?
Can you find that way where you have them both on axial?
So you drew yours both on axial. Okay. So if I drew them, all right, which one? All right, so one of them has to be more stable than the other one. Which is more stable? To have both of them in the equatorial or both of them in the axial?
Both
Equatorial.
Both of them in equatorial. Why?
I don't know the one.
so they don't interfere with each other.
Yeah. So if you guys look, do you guys see how equatorial is all pushed out?
Yeah.
Right. And axials are like a little more bunched up together. So equatorial, when they're pushed out, is more favored. And actually, cool fact, when I have something called 1,3 diaxial, you see how these two methyls are 1,3 of each other? 1 to 3 of each other? We don't want something called 1,3 diaxial, which means 1,3 next to each other, diaxial. So that's going to be bad. So 1,3 equatorial, good. 1,3 diaxial, bad. Okay, so this is most stable. Smiley face. Okay.
Will they want us to draw the most stable, or they just want us to just kind of put something on paper?
And this practice quiz asks for most stable.
Most stable?
Yeah, generally speaking, they preferred the most stable, right? Because the stability is very, very important. Understanding stability and the sterics when it comes to cyclohexanes, very, very important because it helps you understand space. Science space, like, you know, open space. But yeah, so very, very important.
So in this case, just saying.
Uh-huh.
So let's say that first one would have that E, where that first methyl is, with an A.
Okay, let's do that. Let's actually do that. Hold on.
That's the one I drew.
Okay, so let's do it. Let's A, E, A, E, A.
Yeah.
E, methyl, methyl. Okay? When I do that, I get my chair. A. Right? So now I have 1,3 diaxial. This is called 1,3 diaxial. And this is bad.
Okay, so if they were to say more stable, we would just know it needs to just be equatorial.
You're going to prefer, your biggest substituent in equatorial and as many of them in equatorial. Okay? So, this will make sense when we do this one. Okay? So, what I'm going to do is I'm going to draw it both ways. So I'm going to do starting with A and then go around, starting with E and go around, and then we'll compare which one's more stable. All right? So, I'm going to do this one. And let's start with A, E, A, E, A, E. Okay. When I do that, I started with a wedge, so I'm going to switch the dash one to E. And so my chair is going to look like this. All right, so I'm going to call this 1. I'm going to call this 1. All right, bromine is going to be in the axial position. 2, 3. This is going to be the equatorial position, like that. Okay? This is if I start with A. Okay, I'm going to do the same thing, but with E. And then I'm going to do E, A, E, A, E, A. Switch to A. I'm going to draw the chair. Okay, E. Oh, I forgot to draw my bromine here. It's right here. And this one's going to be axial. Okay. Which one is going to be the more stable conformation? First one? I have 1 vote for the first one. What do y'all think?
I think it's
They're kind of the same.
Why are they the same? What do y'all think?
because bromine has priority, so would it not be like for Equatorial?
Why do you say that?
I don't know. I'm going to explain it. That's something you went over with me today.
Yeah, so Con-Eagle Prey law, right? That's going to based on the higher your priority, the bigger you are, right? And we want the bigger thing in the equatorial position. However,
But CH3 is pretty big.
but
too.
CH3 is bigger than bromine because CH3 has 3 additional hydrogens, right? So CH3, even though it's lower on the priority list, because it has more stuff attached to it, it's going to end up more bulky. And because it's going to be more bulky, we want to put it in the equatorial position.
Okay.
Right, so if I were to compare bromine versus fluorine, which one do I want in the equatorial?
Bromine.
Bromine, right? This is the one we want in E. Because their bromine is bigger.
Right.
But just because bromine has a bigger priority, has a higher priority on the KIP, I think is what it is. I don't want to say the whole thing. But just because it has a higher priority doesn't mean that it's going to end up on the equatorial. And and there's a great example of that we might not get to. So, okay, anyway. So the bulkier you are, the more you want to prefer.
So
So,
in this case, the first one.
yes. So the first one, most stable, and that is CH3 Does it make sense?
Yes.
Okay, cool. All right.
Like it makes sense.
So we did questions 1, 2, 3. We did cyclohexanes. We did Newman projections, and we did naming. Which one do you guys want to talk about more? Because we have 15 minutes, but I want to make sure y'all understand this.
Can we do another confirmation?
Cool.
'Cause I'm not.
I'm actually going to cherry pick the confirmation because there's one specific one with special properties that I want to get to. Just give me on page 3. Okay, this one. So let's first name this one.
Which one?
This top one. Okay, so we have, first of all, which one is going to be higher priority on the Kahn-Ingle grid log?
Turbulent.
Yep, okay. Alright, purple, so this is methyl. And then this is going to be 1, 2, 3, 4, 5, 6. Right? So, when it comes to naming, how do I want to do it?
One methyl, one terbutyl. Yeah.
Just pretend if I wrote that correctly. Cyclohexane. And is it cis or trans? Cis. Always remember cis or trans. I actually keep forgetting when I do this, so keep that in mind. All right? Okay.
It only matters when you have these ring formations with the cis or trans. Or
When
so-
y'all like get to alkenes, it matters.
Well,
Cis and
for now.
trans. For now, yes. And it only works when you have only 2 substituents. Like, there's a lot of rules. So we simplified a lot. So don't worry about it right now. Just remember when you have rings and you have 2 substituents, you need to indicate cis or trans.
Okay.
Okay. And so now I'm going to go through and I'm going to draw both versions and we're going to talk about it, okay? So, do we want to do different colors for both versions? I think that'd be cool. Okay, let's do green. Okay, so I'm going to do the first one in green. Okay, so I'm going to do E, A, E, A, E, A. They face the same direction, so I don't need to do any switching. So now I'm going to draw my chair. Okay, I'm going to call this carbon 1. I'm going to call this carbon 1. I have equatorial position, 2, 3, 4, terbutyl and axial position. Okay, and I'm going to do the second version. Blue. And then I'm going to do A, E, A, E, A, E. All right. I'm going to call this 1. 1, 2, 3, 4, 2, 3, 4. Okay, and I'm going to do axial, equatorial. Okay. So, which position is going to be the most stable?
Okay, so she's saying the first one. So first one is that terbutyl is the axial, and the second one is equatorial.
Yes, this is going to be axial.
Okay, so then the second one.
So, which one do we want? Which one is better?
The second one.
Second one. What do you think? Second one? Perfect. And why do we want the second one in the?
Yeah.
Okay? Alright, so actually I'm going to introduce y'all to a new rule. T-butyl always. No exceptions. Because it is so big, right? I drew earlier like how giant it is. Because it is so big, you never draw tert-butyl in the axial position. Even if you end up with everything else in equatorial, in axial. You always want tert-butyl in the equatorial position. Because that gives it the most space. How are we feeling? Good? Alright, so these are the cool exceptions.
Yes. Now I'm like, okay, I'm ready for this quiz now.
Good, good. This is why we have this. So now we've gone through the 3 different types. Let's see, are there any other exceptions I want to talk about? No, we have a second. No. Okay, so,
And it doesn't matter how we count, because I count opposite from you, as long as we are counting in the right carbons.
yes. Wait, what do you mean?
Because
Are you going in
my
the-
chair, I go up over. So I go
Oh, yeah, it
1,
doesn't-
2, 3,
Yeah, it
4.
doesn't really matter.
Okay.
As long as they end up on the current carbons. Questions? Anything else y'all want to talk about specifically on the paper? Anything that you're like, ooh, that looks weird? Y'all get like 8 more minutes, so let's do it. What question do y'all want to do?
Can we name number F on
Oof.
number 1?
Oof. Yeah, you picked a good one. Okay. Boom, boom, boom. Okay, we're going to do this one. Okay, so first things first, let's find our longest chain and count our carbons. So my longest chain is going to be this. Okay. So I have, let's see, 4 methyls. And then I have 1. Okay. So, does it matter which side I count from? Should I switch my numbering?
Not in this case.
No, it's symmetrical, doesn't really matter, right? So I could just go 1, 2, 3, 4, 5, 6, 7, right? Okay. So, all we have to do, okay, what is the 7 called? What is a 7-membered hexane? No, not hexane, heptane.
I keep doing that to make it polyaxate.
Because, like, the 6 is the most common one. It's, yeah, heptane. I keep thinking it's septane because sept is also 7.
Yeah.
I was about to say septane. Like, good save, y'all. Okay, so, alright, so, when we name, which goes first, methyl which goes first, the methyl or the isopropyl, A, B, C, D, F, G, H, I, J, K, L, M. I goes first, so we're going to do the isopropyl first, okay? So which carbon is my isopropyl attached to?
4.
4. So I do 4 isopropyl, and then we get to the cool part, which is all the methyls, and I get 2, 3, 5, 6. Do I say like quad?
I was going to say, is it quad?
Crap. I don't know. I'm gonna say it's called. Wait, no. It's di, tri. I have no clue. I've never. Okay, I think I shot myself in the butt. Okay, it's okay. We're gonna go with it, and then if it's wrong, yikes. Okay, we're gonna say it's 2, 3. We're gonna call it quad methyl, even though I'm not quite sure. Maybe I should Google it. Well, okay, you know what? All right, so I'm gonna put quad, but a big question mark. quad methyl Okay, something tells me I should have Googled this before I did it.
So that wasn't as bad as I thought it was.
Yeah.
It looks scary.
Looks scary, but here's the thing about everything that y'all are going through right now. I know it sounds miserable. I know it's confusing. And on the quiz, on a test, you will get things where you look at it and it's very, very confusing. I drew this specifically to make it as weird looking as possible. Remember, there's steps. Go through the steps. And as long as you go through the steps, you'll know what you're doing. And that's why I really emphasize having a system for going through these questions. If you don't have a system for going through these questions, you'll get confused by everything. That's why when you do Fisher's, right, look at how weird this looks. But we're not going to get overwhelmed by how weird it looks. No, this is Newman, I'm sorry. We're going to get overwhelmed by how weird the Newman looks. We're just going to go through our system and add things on one at a time. If you guys can do that well, and if you guys can go through and organize the way you're doing it, you're going to be faster, you're going to work faster, and you're going to work more efficiently. You're going to make less mistakes because you know what you're doing. And so you can check your work. You can check your work a lot more efficiently.